that now. The best way to prepare for an exam is to look at the previous exams and understand how they work. You'll have 50 minutes to do the exam, and if you look at previous exams, that will give you a clear sense of how much time you'll have to do for what kinds of questions. That's really important, and I've noticed that I've noticed some signs that there may be a few people who are doing things like putting off homework till submission, at 10 o'clock on a Tuesday night. I understand that you guys have other things to do, but of course, planning ahead is really important for things when you're confronting the unknown. And certainly the first exam in any class is an example of the unknown, and you should definitely be careful in preparing early and consistently for this class. It is almost always a surprise for people in this class when they take the first exam, and it's usually when we see like a drop in enrollment, just because it takes some people by surprise. But remember that we can only barely cover everything in lecture, and you can see quite a few things in lab and in homework. But the full expanse of what we're talking about, you have to be sure that you understand yourself. And that means that you need to go to office hours and ask questions and proactively read and reread the lectures to make sure that you understand everything. And read the book if you feel like that's a good alternative source of information. If you see things that you don't understand, test them out on Code Anywhere and find out what they do. Like, you can wait 6 or 7 hours for a response from somebody, or you can test it immediately in Code Anywhere just by modifying your hello world. Sometimes that's just faster. So it's important to start some kind of preparation now, and later on you can prepare even more aggressively just before in a few days before the exam. But don't hold off all of your preparations until a few days before the exam, because you will get a surprise if you look at a practice exam the day before the exam. You'll be like, oh my gosh, this is very different, or not exactly what I expected. And at that point, you don't really have a choice on how you can prepare. So be ready. The Wednesday before the exam, we will be having a review session. The review sessions in this class work as follows. I'll just come and I'll be ready with Code Anywhere, and you guys can ask me any question that you want, and I'll answer them. And if we run out of questions, then the review session will end. But they almost never end early, so that's good. But come prepared. Come with questions about previous exams. Come with questions about specific Java topics that you're not certain about. A lot of the really good questions asked in this class so far have been questions nailing down details. Like, what happens when I have the post increment? And can I have the post increment and the pre-increment together? Or details that seem very small. But it's important to understand that in engineering is all about details. It's all about understanding at the finest level how every little piece of the machine works. Because as engineers, part of what you do is build a machine up to certain specifications that your client or your partner or your boss needs. And not understanding those specifications by overlooking details is tantamount to not doing your job. So it's very important to focus on these details and not feel bad about focusing on them. If you leave those details out till later, then they just become nasty surprises and nobody likes them. Another important issue that I was reminded of earlier today about exams and about what it is to be an engineer is that what you are learning in this class is not simply the subject matter of computer science and the topics of programming. Like, yes, the fundamental subject area of CSE2 is the fundamentals of programming, but what you are also learning is what it means to be an engineer. And what it means to be an engineer is that you understand fully the relationship between what is requested of you and what you must deliver. And in understanding that, your mastery of the English language for discussing technical details and being able to parse and comprehend technical details is an important aspect of that. So the good engineer understands the subtleties of what somebody is saying and understands how to translate those things into technical achievements that need to be done. And unfortunately, when you speak with a client or when you speak with your boss, those people speak colloquially. And when they speak colloquially, then they don't fully detail every technical piece of information that they want, because they either are not technical people themselves, or because those technical things are implied and they expect you to understand them. So one of the challenges of the first exam, which takes a lot of people by surprise, is the fact that there are questions that are asked in a way that is sort of like natural English, in the way that you or I might talk about something being done in a piece of software. Like, this software does X, this software does Y. Now, there are implications to those sentences that are very specific, and these exams are written very carefully to be specific about what you must write. And sometimes I get that wrong. Sometimes I have actually said something that's vague and you can't know if I wanted A or if I wanted B. But almost always, the exam questions are written in such a way that there isn't anything vague, and that if you think about carefully what's being asked for, there's only one thing that you can do. And this is something that you guys need to get used to, because it's not something that you've done before. And that is specifically the translation of English into a specific algorithm for the code. And that's going to be more and more of an issue as this class goes along. Like, in the beginning of the class, there's not that much that I can ask you for that's so complex and maybe slightly vague that it's not clear what you need to write. But you'll see in the second exam that there will be more things that are left implied, more things that you need to infer from what was asked of you that you must write into the code. And you'll see a little bit of that as you prepare for the first exam. But understand that that's a component of this class. And it's not sort of like, oh, I've deliberately left the exam vague so you don't understand. It's deliberately created so that you're being authentically asked for a software product in the way that you would normally be asked in, at a Google, at a Facebook. Yeah. So understand that that is part of the scope of this class as well, because I think when you get surprised by that, it can seem frustrating, because it's easy to think of this class like a math class. Like, oh, I'm going to ask you a question of the form, solve this equation. And math is nice because it's very specific, but engineering is not nice in the same way. Engineering starts with English specifications, and we work out what the issues are, and we come to the final product. And that's something that you guys are going to see in the first exam. And hopefully you will not be surprised by that in the first exam because of that statement. Okay, in the last lecture we talked about selections. And as a part of talking about selections, we needed to talk about comparisons. And we talked about numerical comparisons, so that was good. If you've been maybe reading along in the book or looking at other resources online, you now have a clearer understanding of what comparison operators are and how Booleans work together. So we need to look now at a different kind of comparison. That's the comparison of strings, and different variations on selection statements. So we've seen the if statement and the if-else statement, and now we need to see some of the other variations so that we understand all of the different tools that are available. Okay, so let's just start with a little bit of a reminder. Remember that when we compare strings, strings are a special class of operator. Excuse me, this is an old slide. So remember how yesterday, or on Monday, I tested that the version of Java that you're using in Code Anywhere will allow for the equality test on strings. there's this equality test that you can use on strings is now equivalent to this equality test. So on old versions of Java, you had to use this, and using this would lead to an error. And at some point, more recently, the uprising about this aspect of the syntax of Java was such that the people who sort of govern the next version of Java decided, all right, we're going to cave to this, and we're going to allow testing string equality with a double equals b. So, sorry about this old slide. I should have taken it out, but you can test string equality with a double equals b, or you can say a dot equals b, and both generate true if the strings are the same, and false otherwise. In fact, I'm going to do this just so that those people looking through the lectures later don't get confused. Okay, so the next thing we need to learn about, and this is a very important operator, is the modulus operator. The modulus operator is the remainder operator, and it works by giving you the remainder of the division of the two operators. So when I divide 5 by 3, I have some remainder, and using the modulus operator, 5 modulo 3 gives me the remainder equal to 2. So this seems like it's kind of an obscure operator. After all, we didn't introduce it with the rest of the arithmetic operators, right? But it's used very frequently in Java. And not just in Java, it's used very frequently in computing. And the reason why it's used very frequently is because it allows us to do modulus operations. So one of the things that we frequently want to do is we want to have the computer iterate over a series of instances of something, a list of objects, a set of containers, or a set of individual things. And we wanted to have it go over and over and over that same list. And usually we have some name for the things in those lists, like the first thing, the second thing, the third thing, and the fourth thing. And we need to come up with which thing we want the computer to look at next. So if you think about how the modulus operator works, if I had 1 modulo 3, that'd be equal to, that would give us a remainder of 1, because 1 divided by 3 gives us a remainder 1. Because 1 divides 3 0 times. 3 divides 1 0 times. So 2 modulo 3 would give us the remainder 2. 3 modulo 3 gives us the remainder 0. Right? Also, 0 modulo 3 gives us the remainder 0. So if I look at the increasing positive integers, then those values are going to, as I compute them modulo 3, those values are going to give us 1, 2, 0, 1, 2, 0, 1, 2, 0. And the importance of that is that that allows us to specify the 3 objects over and over again as a loop, as an iteration. And that's used frequently in Java to basically walk over the same list over and over again. And that's something that we'll see later. But that's why we use the modulus operator so frequently in computer science. Question back?
What kind of precedence does this operator have?
Great question. So it is an arithmetic operator, and it is the same as multiplication and division. So you can consider it just at the same level as multiplication and division, and so it's going to be left associative as well, because it is an arithmetic operator. So if it's mixed in with other arithmetic operators, it will also have left to right associativity with them. Yes?
And you kind of like went over it, like what's the main point of this again?
So the main point of the modulus operator is that it allows us to wrap around a finite set of numbers or objects. So in this case, imagine that I had 3 objects, and you know, like maybe they're like maybe there are 3 people that are doing a job and I'm managing them, and I don't want to have anybody overworked. So I'm going to say the first person you go, second person you go, third person you go. Now the first person you go, second person, third person. So to have the computer do that, we have to have some way of going round robin like that. And the only way to do that is, or the most convenient way to do that is using the modulus operator. And the way that that works would be to have the computer simply have a number that increments every time, like 1, 2, 3, 4, 5, 6, 7, and then compute the modulus of that counter value. So in this case, imagine that my counter was equal to 1. 1 modulo 3 is 1. If the counter increments, then it's 2. So 2 modulo 3 has remainder 2. And then when the counter increments again, the counter is equal to 3. So 3 modulo 3 is equal to 0. So the 0 could be the first person, I guess. And then 4 modulo 3 is equal to 1. 5 modulo 3 is equal to 2. 6 modulo 3 is equal to 0. 7 modulo 3 is equal to 1. And so the result is that we just keep walking around that circle. So if I have a circle of 10 people, then I start calculating things with like x modulo, counter modulo 10. So then it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And so that's a really convenient way of having not just counting, but even mathematics on this kind of thing. So imagine that we had this group of people where, again, they were going to do jobs in a round-robin way. Suppose I wanted to know who was going to have the job in 3 steps. Well, I could say, take the current counter plus 3, and the sum of those things, quantity modulo 3, would be who has it in 3 steps. And so that would, in the case of modulo 3, it would be the same thing, but in the case of modulo 7, we can still calculate that, because we can just figure out how far would the counter be modulo 3.
Yeah.
And that tells us exactly who would be going there.
So you're assigning the number to each person, basically.
Yeah.
Okay.
Yeah. So that's a really simplistic example, but there are many cases where we want to have mathematically something that wraps around.
Mm-hmm.
And that wrapping around isn't simply with counters, but it's with we have to do sometimes mathematics on the current person. So saying who's gonna go in 10 steps is exactly what we want to calculate then. It'd be like the number plus 10 modulo 3 gives us the index of the person who would be going. So that's just a taste of what the modulus operator does, and we'll see this a lot. We'll see this a lot, especially in the middle section of this class, where we're going to see loops. So just a taste about loops. We've seen how if statements let the code divide, right? If it's true, then go on one side. If it's false, then go on another side. Run that code instead. What loops do is they simply allow the code to go in a circle, so just keep running over and over again. And one of the most important things for that is controlling how the loop works. And the modulus operator allows us to have the loop always work on a finite set of things. So if it's like some sort of electronic merry-go-round, and you're like turning on the horse on each part of the merry-go-round circle, and you only have 5 horses, then the modulus operator allows us to turn on the right horse each time we shift the turn of the horse or something like that. It's an arithmetic operator, so it can be used in many, many different ways. And you'll see examples of it in homeworks and labs and elsewhere. But more specifically, understand how it works and be comfortable with it, because we'll see it again. And eventually, in the 3rd section of this class, when we have arrays, you'll need to be able to use the modulus operator as a problem-solving tool. And it's really a great problem-solving tool, although I understand that right now, having just learned about it, it's not obvious why you would use it to solve your problem. We'll see about how you can do that later. Okay, so there are some other things that we need to know about that are just sort of utility functions that will it'll help you do other interesting things. So one thing that you can do with Java is request the current time. So that's basically having the computer check its system clock and have the system clock tell you what is the current time. And what the command system.currentTime millis does is it tells you the number of milliseconds that have happened since midnight, January 1st, 1970. So that seems a little bit random, like why January 1st, 1970? This is sort of in computer circles referred to as the epoch time. This is, it's sort of thought of as a universal point where we can start counting time. Because otherwise, when do we start counting time, right? Do we do it January 1st, 0? Or when exactly will we do it? It's convenient to count milliseconds since then because it's not too many milliseconds. And it's also a period of time when generally there were no computers before 1970, and so you don't really have to worry about what happens if I have negative time. So this simply gives you the current time in milliseconds since 1970. Now, one of the things that you can do with current time millis is that you can compute this number, which is some large number, right? And you can compute it modulo 10 to get a semi-random, uncontrollable number from 0 to 9. Because remember, anytime I compute remainders with some number, say that's x, the set of remainders are 0 through x minus 1. I can't divide something by 10 and have a remainder 10 because that wouldn't be a remainder anymore. So when I'm computing integer modulus, this is going to have this is going to be a value from 0 to 9. When I compute the modulus 10 of the current time in milliseconds since January 1st, 1970, then that gives me sort of this very quickly rotating clock that gives me a value from 0 to 9. It's sort of like looking at the last digit of a stopwatch, right? It's sort of flickering really fast through those digits. And that can be a sort of a cute way to set up an interesting program. Like you can have a program that is sort of like the stopwatch game. It's like when I hit stop on the stopwatch, you're going to guess what number is going to end up on the rightmost digit, and see if we can guess that. So you can imagine having a call to current time millis and computing the modulus 10 of that large number, and get that number out for somebody to guess. Okay, so that's a way of getting a kind of a random or a constantly changing number, right? Because depending on when the user, when Java hits this line, system.currentTime millis modulus 10, the program could get a different value, right? Like sometimes the program could get a 0, sometimes the program could get a 5, or whatever, depending on exactly which millisecond has happened, depending on exactly what millisecond the system hits that particular timer. Yes?
So I'm confused. Is like the clock constantly run while the code is running? Or
Yes.
does it just stop when you run the code?
That's a great question. So how does the system clock work? So in the computer, the clock is constantly running. It's one of the things that the operating system is taking care of, actually. So as a programmer writing an app, you are able to dip into some of those resources that the computer has. So one of the things that you can do is ask what time it is. So sometimes you want to do that for the most basic reason, like you want to show on a window your user what time it is. But other times you want to use it to time internal processes yourself. Like for example, any email client that you use, like your email app, it has a timer that it's gonna request an email from the server. And if the server doesn't get back to it in 10 seconds, it's going to stop waiting and be like, problem connecting to server. And in order to measure that time, you actually have to, you need to get a number that says, I started waiting now, and I'm not waiting until after this time. And the only way you get those numbers is by asking the system clock. So the system clock becomes this nice reference for exactly how fast the computer is doing things inside the code itself. And that happens a lot, especially with user-facing applications, because you want to make your code return things in a responsive way. And anytime you know that you're running a calculation or something that might take too long, it makes sense to check periodically how long it's been since you ran, and then you could, like, you know, if you ran too long, you could ask the user, like, oh, this is taking a while, is it okay? Or something like that. So, but to get to your specific question, like exactly what is the system doing? The system literally queries the hardware and gives you a number. It does some calculation, but it gives you this number that is the current number of milliseconds since that time. And this basically gets evaluated as an integer, and you get this number back. And it will be different every time you call it, because the number of milliseconds since that time has been more milliseconds since then. So this is interesting because in the code that we've written so far, everything seems to be running very quickly. It seems like there's no real sense of time, right? Like we hit enter and then everything just runs, and unless it's waiting for the user to type in something, the program runs more or less instantly. Later in this class, you guys will run like really long programs that could run arbitrarily long, and that's when this sort of current time in milliseconds becomes really important. Yes?
I'm not sure if it was implicit in your question, but does it store the value at the time that you compile the code or when you run it?
It stores the value or requests the value of the current time in milliseconds when you run it. So the next time that you run it, it's going to give you a different number. Great. So this is a way, now you can see how running your program at different times is therefore going to yield different results, right? So there's another way to cause your program to yield different results when you run it at different times, and that's by generating random numbers. So generating random numbers is really, really important in computing because we need to be able to produce random distributions of points in intervals for security reasons and in order to obscure data. So let's explain how random numbers work. So current time in milliseconds is not that random, right? It's just a way of getting your code to produce different output at different times. It could seem random from the human perspective because every time you run it, you've run your program, it's sort of been more than 10 milliseconds. So it seems like you're going to get sort of a random number there, especially if you're computing the modulo 10 of current time in milliseconds. But it's not exactly random because you can have the computer run current time in milliseconds very, very rapidly. The computer is far more rapid than running a command every millisecond. It's running commands, it's running billions of commands every second. So for the computer, if you ran current time milliseconds really quickly, it would simply give you the same number. It would be like 44444, and then 55555, and then 66666, because if I keep computing the current time in milliseconds modulo 10, it's going to run multiple current time millis calls every millisecond. Because remember, it runs commands on the order of billions of times per second. So that means millions of times per millisecond, right? So that means that if we want to produce more evenly distributed outputs, we need something that's going to really cause the computer to do different things. And that's where random number generators come in. So if we need a random number, we can use the math method random. So that's literally math.random. And that generates doubles in this interval here. So this interval is not my bad typing skills. This interval is defined as the hard value 0 and the soft value 1. So math.random generates doubles which can include the 0.000 number, but they cannot include 1.0. So this is everything from 0 to 0.9999999. And it doesn't seem like that useful, right? Because it's just a double value between those two intervals. But the way that we use that is that we can multiply that double value by some other number in order to get any random number that we want. So for example, if I have math.random times 10, excuse me, math.random gives me a value from 0 to 0.9999, and when I multiply it by some other number, say 10, that now gives me a random number from 0 to 9.999, right? So, and I can cast that to an integer, so that's going to give me random numbers from 0 to 9, including the 9. So that's a great way that I can get a random number in some interval range, an integer range. In fact, imagine the way that I can use this. Suppose part of what you needed to do in a program that you wrote was give me a random number from 7 to 15. How would I do that, right? Well, 15 minus 7 is 8. So what I really need is a random number from a random number between 0 and 8, 0 to 7.999. And then I can add 7 to that to give me a random number between 7 and 15, right? Because those random numbers from 0 to 8 plus 7 give me random numbers in that range, 7 to 15. So that would be sort of like adding a value to the random number after I multiplied it by 8, and that would give me random numbers in that interval. Using this interval 0 to 1, I'm able to generate random numbers in any arbitrary interval that I want. And that's really useful for producing random numbers in controlled intervals that I want to use for my particular program. So it could seem initially like this is kind of useless, that, well, if it only gives you random numbers from 0 to 1, then what am I supposed to do? But just a little bit of math on that random number operation allows me to place those random numbers in the interval that I want. Okay, so later on, after you get comfortable with using random numbers, it's good to think about how these random numbers work. So one of the crucial usages of random numbers is to generate passwords. Because you know exactly at what point the random number was generated, you can sort of, you can always dependably calculate the same random number with the same inputs. Excuse me, let me backtrack. The random number function is not purely random. As you know, computers can't generate purely random numbers. They generate what are known as pseudo-random numbers. Pseudo-random numbers are not random at all. It's really just a complicated mathematical function that takes a number as an input and generates a number which appears random as output. So the number that the random number takes as input is usually the last random number that it generated. And that means that you're taking a random number in, and you're generating another random number out, and they seem unrelated, and that's great, because that gives you a whole bunch of sort of apparently random numbers. But if you know the random number that went in, you're guaranteed to get the same number out. It's not random at all in that sense. If I give it a number in, I'll always have the same number out. And that fact is used to generate secret passwords. So what actually happens when you guys make a new account on Google or Snapchat or whatever, when you give it that password for your account, it takes those letters and translates each one of the letters for your password into a random number. And that random number is what actually gets stored. And because somebody who reads that random number doesn't know the exact criteria under which the random number generator generated that random number, they don't have a way of easily going from that random number back to the letters that you use. So it becomes a great way of obscuring between two people, or two pieces of software in this case, the exact password, even though you can verify the password. We'll have some cool assignment/lab stuff related to that fact later, just so that you can learn a little more about it. Okay. Now I said that we were going to learn a different kind of, yes?
Okay, just a quick question about the random numbers. So like when we like do the formulas, I guess, to create them, like could you sort of just, I I don't know, like, I kind of need a little bit more of an explanation on like how exactly we figure out which numbers to use for like, you know what I mean, like plugging in, like what they do if you plug in.
Sure.
Sorry,
No,
that
don't,
question was phrased.
don't apologize.
Sorry.
That's a really good question, and I'm happy to expand on it. So, if you want to make a random number in any interval at all, then there are two issues to know about. So first of all, that interval doesn't necessarily start at 0, and that interval has some width, right? So when I have a tool like math.random that generates an interval from 0 to 1, then I need to stretch that interval to be the right width, and then I need to slide that interval to start at the right point. So if I have a random interval, if I want to make random numbers between 5 and 10, or let me do something a little bit more, between 20 and 30, then I know that the interval is not starting at 0, it starts at 20. And also that the width of the interval is 10. So I can start off by generating random numbers from 0 to 10 by multiplying the values from 0 to 1, generated by math.random, by 10. So this expression here gives me random numbers from 0 to 10. But those are random numbers from 0 to 10, not from 20 to 30. So to get the offset, I add everything here by 20. And that's not an example, but if I can slide that whole interval over by 20, and that gives me the interval, random numbers interval 20 to 30. Okay.
Yeah, thanks.
Yep. Oh, and another thing is that if I want to generate integers from 20 to 30 and not random doubles from 20 to 30, I can cast that to an integer. So if I wanted to generate random floating point values, I can translate those to floats by casting. Okay, so regarding the multi-way if statements, there are cases when you're dealing, especially with user-facing code, with many different possible inputs that you can get from the user. Your keyboard is the best example, right? There's a case where the person presses A, there's a case where the person presses B, and so on and so on. So there are many cases when you just have software that's dealing with a lot of different cases. There aren't an infinite number of cases, there's just a whole bunch of cases. So, maybe I've got some registration software that is handling registration requests from different students. We've got undergrads, we've got grad students, maybe they have different statuses or whatever. We have different cases for all of those different students. Not an infinite number of cases by any means, but you might have not just 2 or 3, you might have a few dozen. And writing the if statements to cover all those cases can be tedious. And when it's tedious, we have a tendency to write errors. We have a tendency to write bugs. So one of the most important things to learn as a programmer is that you should be sensitive to what conditions you are more likely to write a bug in, and be aware that one of the most likely cases of writing a bug is when you have to do something long and tedious. So this code here is tedious in the sense that it's repetitive, and yet it changes a little bit each time. And the most likely way that I'm going to make a bug, and probably the case the same for you, is that I'm going to cut and paste the else-if parts over and over again, and then I'm going to change each line, right? But I might accidentally forget to change something, either in what gets printed out or in the number that gets checked, and so I could make a bug job. So there are reasons why we might not want to have these long multi-way if statements, and those if statements can be a hassle. So we have an alternative for writing them in a much more efficient way that doesn't have as much tedium. Yes?
Are you also missing brackets in that?
Yes, I am. This is stylistically bad code that fits on the screen. So yes, there should be brackets here. Now, technically this code will compile and work the way that you might expect, but stylistically you should always have the curly braces after each if statement. Yes?
You'd only have the curly braces at the very beginning, or after the first if and at the very end, right? Not between every else if.
You could actually have curly braces after the else and after, like before the next else, basically.
Do you have to?
You don't have to. Now, I generally don't recommend separating else ifs with curly braces because most people understand how else if works. Although it can be made in a really confusing way. And if for your entertainment, if you Google Java obfuscation contest, people write code in deliberately hard to read ways that just abuses the acceptable syntax. So they write code that works, that compiles and actually functions, but it's like literally impossible to read. And once you have a look at like the crazy tricks that they pull in order to get Java to look crazy, then you'll learn, or then it will be more obvious to you like why it is that we have these like conventions for writing code, even though it's not technically required. Yes. What's your name again? I have to keep asking names. Abby.
Is there like a way, like later down the line, like I know we're like at like the basics of this, to make the code kind of recognize a pattern and like instead of having to type in like else if 2 equals 2 equals 3 equals 4 and like have the same thing with like one thing changing, like to do that itself?
Yes, there are. So we're going to see one way to have it be simpler, but it's not a lot simpler. And if you remind me in October, I know it's like it's a random number.
Yeah.
If you remind me you know what? It'd be more like November actually. But if you remind me in November, I promise you I will show you a way to make this way simpler.
Okay. Thank you.
Sure. Okay. So the way that we simplify large blocks of if-else code is by using a switch statement. And the switch statement is something that you need to be aware of because the switch statement is really powerful, but it also has some things that can cause issues if you don't know exactly how it works. So this is how the switch statement works. It's a different piece of syntax. It's also a kind of a code container, but it has a special structure to it. So it's always started with the word switch, and it's followed by parentheses that hold, an expression, the conditional expression for the switch. And there can be several different types of there. There can be chars, there can be ints, there can be shorts. There can be other values in there. There can't be strings. But basically, these expressions are values that can be casted into an integer. That's followed by curly braces. And then inside the curly braces, we have this special syntax construct, case space value 1 colon. You have to have that colon there. You must use the special word case. And the value is a specific value. So imagine that we had a large block of if-else statements that dealt with the number of years a student was at Lehigh. So you have the case for the first-year student, the second-year student, the third-year student, the 10th-year student. And in order to handle those things, we'd have case 1, case 2, case 3, and each one of those statements would be executed if that particular case was equal to whatever was passed into the switch. After those statements get executed, you have this word break. Now this break here is optional. The cases and the switch, that's not optional. The break here is optional, and that causes the switch to do things that you might not expect. I'll explain that in a little bit, but just understand that this is optional. And there's a special case called the default case, which doesn't have a value after it. And what the default case does is that it always runs if if you haven't activated some other case. Okay, so let's look at how we translate the if statements into a switch statement. So here I've got a block of if statements, else if statements, and imagine this is the students with the different number of years that they've been at Lehigh, I guess rounding up. So here we're going to print line that a person's a freshman, sophomore, junior, senior. We can convert that to a switch statement, having case 1, print line freshman, break, case 2, print line sophomore, break, case 3, junior, break, case 4, senior, break. So you can see how that eliminates the complexity of curly braces inside all those else if statements, right? So that the awkwardness of like, do I need to have a curly brace here, yes or no, that becomes compacted down to just simply the switch statement with different cases. So that's really nice. And that means that I can write these cases without dealing or worrying about the tedium of exactly where my curly braces were. I can have this work the way that I expect. In other words, if the variable student, which might have been inputted through a scanner, or might be just hard-coded into the code, if the value stored in the variable student is equal to one of these cases, then it's going to execute the code in that case. And that's the way that we want our switch statements to work. It's going to give us the code that corresponds to the case that we want. Okay, now, there's something about switch statements that is different from if statements. And that is that they allow something called case fall-through, which cannot happen with an if-else block. Case fall-through occurs when you decide not to use the optional break statement. And that's because the way the switch statement works is a little bit different. So let's review exactly how this works. When Java sees a switch statement, it's going to get a value in the student variable. And then it's going to start looking at cases. Let's say that student is equal to 3. It's going to look at case 1. And if case 1 is not equal to student, it's not going to activate the case. And then it's going to look at case 2. If it's not equal to student, it's not going to activate the case. And in the case of case 3, when it is equal to the student, then it's going to activate this case, meaning that it runs the code inside the case. And then when it hits break, that means that the code in Java will continue to the end of the curly braces. It's not going to hit anything else. So no other code after the break statement gets run, and the next line executed is the first line after the curly braces. That's what the break does in the statements. Now, remember, I said the break is optional, so if a case is activated and it has no break statement, that means that execution occurs into the next case. And that is really, really counterintuitive, and it seems, like given the most default example here on the right, it seems like that is just a way of making bugs and it doesn't really help a lot. But the reason why we might want that to occur is that we might want some things to always flow into another case because the two things handle things that are related. So what the switch does is it gives you more control than the if-else block. But it gives you the risk of coding a bug. And that bug has to do with the existence of the break statement. Now, just to make sure that everybody is very clear on how exactly that break statement works, I'm going to give you examples of horrible switch statements that have some missing breaks, and they will force you to think very carefully about when a case runs and when a case doesn't, and if it falls through to the next case. But understand the process by which we figured out how the switch statement works. First, we get the value, and then we start scanning the cases. Now, in this case, if student is equal to 3, we scan the cases until we hit a case that's equal to the input value, and then we activate that case. So then we start running the statements inside the case, and if we hit the break, then we exit. And if we don't have a break there, then we're just going to continue to the next case, and we're going to continue following through to subsequent cases until we hit a break or until we get to the end. So imagine that these two breaks are gone and student was equal to 1. Then we're going to print line freshman, and then we're going to go into the next case, print line sophomore, and then we're going to go to the next case after that, print line junior, and then we're going to hit the break and exit. And that might not be what we want, but that's what the code is going to do if it doesn't have these two breaks in it. Okay? So that's case fall through, and it's critical to understanding how switches work because of that. And note that you can fall through to the default case, because the default case automatically activates